So now it's time to formally define a limit. We really haven't done that yet. We've talked about what it is, we talked about how to find it, but we never actually formally defined what it is. And so here's a formal definition of a limit. It's also called the delta epsilon definition of a limit. So let's read it. Let f be a function defined on an interval containing c, except possibly at c. Remember, it doesn't have to be defined at c, it just has to be defined around c. And let L be a real number. The statement, the limit as x approaches c of f of x equals L, means that for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Now, you could read that probably a couple of times and it probably won't sink in what it really says. But what it's saying is the exact same thing we've been saying throughout talking about limits. And so the idea is this. All right. Delta and epsilon are distances. Okay? Delta is the distance away from C. Okay? So if you have this value C right here, and that's what you're trying to approach from both sides, you want the distance between your x values and C to get smaller so that you can get closer and closer to C. And that's what this is saying. The absolute value of x minus C right here is basically talking about the distance between an x value and C. And if that is less than delta, which is an arbitrarily small value, then this means you're getting closer and closer to C. So it's basically talking about this piece. Okay, so once you have that, it's nothing different than what we've been talking about. You got to get close and close to the C value from both sides. It says then the absolute value of f of x minus L is less than epsilon. Well, this is talking about the distance between f of x and L, the y values and the limiting value. That's what this and this are. So the idea is when we get closer and closer and closer to this y value, they have to get close to the same y value from both sides. Well, epsilon is the distance there. So f of x is these arbitrary y values here, here, here that we're approaching this particular y value. And the same thing here, here, and here. And the distance here between each y value and then the thing we're getting closer to, that limiting value, that distance is epsilon. So the idea is what this whole thing is saying, which is the same thing we've been saying all along, is that when you get close to C, you have to get closer and closer to L. Okay? That when x approaches some constant value, or even infinity, okay? But when x gets closer and closer to C, then the y values have to get closer and closer to L. And if that happens, then L is the answer for this limit. So it's really no different than what we've been saying. This just puts it into words in terms of delta and epsilon. So the first person to mathematically assign this meaning using this delta epsilon was Cauchy. Okay? Cauchy is a famous mathematician. He was the first one to really come up with the delta epsilon definition. It's the same definition we pretty much keep using today to talk about a delta epsilon definition. Now we can talk about what we call a delta epsilon proof of a limit, and we'll look at one quickly. This is usually reserved more for higher level mathematics, but we can talk about it now. Right now, all I need you to be able to do is to understand how this statement right here, okay, which says again, here, I'll erase all this, which says again that this limiting statement, when we say that the limit as x approaches c of f of x equals L, what it means is that for each epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. When we get close to when x gets close to c, f of x gets close to L. So here's an example of a fairly simple use of that definition to prove a limit. And so here we go. Here's the limit as x approaches 2 of 3x minus 5. And that limit equals 1. Okay? Why? It's because this is one of those ones you could just plug 2 in. You plug 2 right in there for x, you get 6 minus 5 is 1. Okay? Because the function value and the limiting value are the same. So what we want to do is we want to prove that this limit does in fact equal 1 using this delta epsilon definition. So you must show that for each epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c, in this case is 2, is less than delta, then f of x, which is 3x minus 5, minus L, which is 1, is less than epsilon. Okay? So when we look at it, this statement right here is using the f of x minus L. This is f of x, this is L, and this statement right here is using the x minus c, c being 2. Okay? So we need to work with the relationship between f of x minus L and x minus c and use that to prove that this happens. So we basically have to decide what epsilon and delta relationship are we going to use. In this case, we're going to say that delta equals epsilon over 3. Okay? Why? Essentially because it works. Really what you do is you kind of work this proof backwards and then you do the proof forward. So if we work with the x minus f of x, the x minus c is less than delta statement, and we let delta equal epsilon over 3, what happens? You get x minus 2. The absolute value of x minus 2 is less than delta, delta being epsilon over 3. And then we start working with this statement, and we want this statement to essentially give us this. If this happens, then this happens. So if we let delta equal epsilon over 3, can we make this here, this f of x minus c is less than delta, give us f of x minus L is less than epsilon? And it will, because of the delta that we chose. So we'll multiply this 3 to the other side of the inequality. So now we have 3 times absolute value of x minus 2 is less than epsilon. Then I can distribute this 3 into the absolute value. So we get 3x minus 6 is less than epsilon. Then I can break the minus 6 apart into minus 5 and minus 1. Here's your f of x, here's your L. So we have basically the statement that the absolute value of f of x minus L is less than epsilon. And it was all because we conveniently chose that epsilon over 3. Now, how did I choose that epsilon over 3? Really what I did is I started with this statement here. 3x minus 5 minus 1 is less than epsilon. And I kind of started working this backwards to try and get myself to here. So I actually did the subtraction, which gave me the 3x minus 6 is less than epsilon. Then I factored out the 3, and I had x minus 2 is less than epsilon, then move the 3 over, and I see that, okay, I got this statement, absolute value of x minus 3 is less than something with an epsilon in it. So if I let delta equal this, then I know if I work it backwards, I can get to here. It seems like cheating. It's not. It works out nicely. Why? Because the limit actually exists, and this is easy to prove because it really is true. Also, this is an easier delta epsilon proof because we're working with fairly simple functions. I mean, we're taking the limit of this linear function. It's a very simple one. It's a little bit more complicated if we do some fairly complicated functions to prove limits. And like I said, a lot of this will be reserved for higher level mathematics. But this is just your introduction to the idea of a delta epsilon proof for a limit. Largely, we will be using the analytic approach to find the value for limits. This is basically after you already know the answer for the limit to prove that it is in fact the answer. You could use this delta epsilon proof.